Hello, and welcome to Field Lab Earth, the podcast that's all about past and present advances in the fields of agronomic, crop, soil, and environmental sciences. Today, we'll be talking to Dr. Dan Ferreira about the Fukushima Daiichi Nuclear Disaster. 10 years ago, a massive earthquake and tsunami led to the explosion of 3 nuclear reactors at the Fukushima Daiichi Nuclear Power Plant. The explosions resulted in radioactive particles being released into the air, which eventually settled on neighboring soils. Dr. Ferreira has been working for half a decade to study these soils, including the bonds forged between these materials, the strength of those bonds, and, most importantly, how to break them. We'll talk more about that in a minute, but before we dive in, we did want to thank our sponsors, starting with Gasmet Technologies, the maker of the GT5000 Terra, the smallest portable FTIR multi-gas analyzer for greenhouse gas and environmental research. Measure carbon dioxide, carbon monoxide, methane, nitrous oxide, nitric oxide, nitrogen dioxide, ammonia, and water vapor in real time simultaneously from static or automated chambers. Visit www.gasmet.com, that's Gasmet spelled G-A-S-M-E-T, or email sales@gasmet.com for more information. Our second sponsor is Meter Group. Meter specializes in robust soil moisture sensing, innovative weather monitoring, cloud data logging, advanced data visualization software, and more. Their well-published scientific instrumentation is used worldwide in universities, research and testing labs, government agencies, agriculture, and industrial applications. Find world-class webinars about the science behind environmental measurements at metergroup.com/fieldlabearth. I'm your host, Abby Morrison. Let's talk about science. Hi, everyone. Welcome to the show. Today we have Dan Ferreira with us. Dan is an associate professor of environmental science at Kennesaw State University in Kennesaw, Georgia. He received a bachelor's degree in environmental science from the University of California at Davis and a master's degree in geological sciences, as well as a PhD in soil science from the University of Connecticut. Dr. Ferreira has been researching contaminated soils in Fukushima since 2016 and has been researching soil pollution in general since 2008. Hi, Dan. Welcome to the show. How are you doing today?
Doing great. How are you?
I am doing super. So excited to talk to you today. We are going to be talking about the Fukushima nuclear disaster today and some contaminated soils that you've been working on. So to get started, can you just give us some background about what happened at Fukushima, just like an overview of the events? Let's start there.
Okay, so on March 11th, 2011, so 10 years ago this March, the Tohoku earthquake hit Japan. This was the biggest earthquake ever to hit Japan, and it was actually the 4th biggest earthquake in recorded history. So since we started keeping records, this is the 4th biggest earthquake we've ever seen. It happened about 40 miles off the coast of the main island of Japan, Honshu, and the earthquake was actually so big that it moved the entire island of Japan, the main island of Japan, 8 feet to the east. So that earthquake created a tsunami that was enormous. In some areas, that tsunami was actually recorded to be as tall as 130 feet. So the earthquake and the resulting tsunami was an enormous natural disaster. A little over 18,500 people died from the earthquake and the tsunami, and there were over 1 million buildings damaged to one degree or another. 122,000 buildings were totally destroyed by the tsunami that was created by the earthquake. The damages from both the earthquake and the tsunami were estimated by the World Bank to cost about $235 billion, which actually makes this earthquake and tsunami the costliest natural disaster in history. So the main result of that earthquake that caught global attention was when the tsunami struck the Fukushima Daiichi nuclear power plant. So that power plant, being close to the ocean, was actually designed with a seawall, but the tsunami was much, much bigger than the seawall was designed to be able to handle. So when that tsunami hit the power plant, it topped the seawall and flooded the plant. The biggest problem with that is that it flooded the diesel backup generators that were powering the pumps that were supplying cooling water to the reactor. So when the earthquake hit, the power plant is designed with all of these safety systems. And when the earthquake hit, the nuclear reactors actually shut down. But despite the fact that they were shut down, you have to keep cooling water circulating to those reactors, because even after you shut down the fission reaction, the reactors themselves stay very, very hot. So it takes a long time for the reactors to actually, after they've been shut down, to cool down enough that they're safe. And so in the event of a natural disaster like this, there are backup generators that supply power to those pumps that pump the cooling water. But because the diesel generators got flooded, they shut down. So once those cooling systems failed, the reactors started heating up, and they heated up beyond safe levels, and that eventually caused 3 of the 6 reactors at the power plant to explode between March 12th and March 15th. So over the course of those 3 days, 3 of those reactors exploded. And those explosions caused small particulates, so little tiny bits of material that were laced with radioactive residue, to get ejected way, way high up in the air, and they were then carried by the prevailing winds and deposited over a significant area across Japan. So those particulates are very light, and the explosion lifted them up, but eventually what goes up must come down. And so when those particulates eventually fell down out of the atmosphere, they were deposited onto soil or onto water, depending on where they fell, and they then contaminated the soil and the water with the radioactive isotopes that the particulates were carrying. So there were a lot of different radioactive isotopes that were ejected from the power plant during those explosions, but the most worrying one was cesium-137. So the problem with cesium-137 is that it lasts a long time. Other radioactive isotopes, they break down very quickly. So, for example, iodine-131, which a lot of people hear about after a nuclear disaster because it's very, very radioactive, it has a very short half-life. So iodine-131 has a half-life of 8 days. So what that means is that after 8 days, half of that iodine-131 has broken down and decayed into something less harmful. Cesium-137, in comparison, has a half-life of 30 years. So you can see why a lot of the research after the disaster has focused on cesium-137 contamination in the areas downwind of the plant.
Sure. Yeah, that is a great overview. Obviously very sad. I didn't realize like the extent of the tsunami and the earthquake. Like I remember hearing about Fukushima and the power plant, but I don't feel like I was as cognizant of how horrible the natural disaster itself was. So yeah, the soils, you mentioned that as well. We will get to that more in a minute. But before we get there, I also did want to ask you kind of how you got involved in this research. Obviously, Georgia is not super close to Japan. So can you tell me more about like what got you involved in this research in the first place?
Sure. So this is one of the great things about being a part of an academic society like the Soil Science Society of America, is that you get exposed to a lot of different people from all over the world. And at one of the meetings of the SSSA, the 2013 meeting in Tampa, I was looking through the booklet for the different sessions at the meeting, and I noticed that there was a session on radioactive soil contamination in a farming village called Iatate Village, which is in Fukushima Prefecture. So the session was grad students from different universities in Japan who were going to be presenting on some of the research that they had been doing in Fukushima to try and help these farmers whose soil had been contaminated. And it grabbed my attention. I mean, it seemed like such an interesting thing to learn about. So I went to the session, and as I was listening to the presentations about the radiocesium contamination, I became very interested in what was going on chemically in the soil, because the phenomenon of what was going on with cesium in Fukushima was actually very, very similar to some of the research that I had done as part of my doctorate, looking at soils contaminated with sodium. In the Midwestern United States, in places like North and South Dakota, Utah has a lot of this issue with sodic soils. So the mechanics of what was going on in the soil in Fukushima was actually really, really similar to the work that I had done for my doctoral dissertation. So after the meeting, I came back to my university here in Georgia, and I started kind of doing some more research into what was going on and how they were dealing with it. And a few months before the next year's meeting in 2014, I emailed Dr. Kosuke Noborio of Meiji University. He was the person who was in charge of that session at the meeting in Tampa. And I just said, hey, I've been, thinking about some of the stuff that I learned at your session last year. I'd love to take you out to lunch and talk about some ideas that I've had. And so when I went to the meeting the following year, I went out to lunch with him and his colleague, Dr. Mizoguchi of the University of Tokyo, and just kind of talked to them about how I was interested in what was going on and how it tied into the work that I had done and kind of some of the ideas that I had been rolling around in my head. And they invited me to come to Japan, and they said, come, we'll take you to Iatate Village, we'll show you around, show you some of the research that we're doing, we'll introduce you to some of the farmers so you can talk to them and meet them. So in 2016, I was invited to Japan as a visiting scholar at Meiji University. And so I went there for 10 days, and they took me to Fukushima, and they showed me around, and I was just I at that point, once I met the farmers and talked to them and really kind of saw firsthand what was going on there, I decided, like, this is it. I have to get involved. I have to do this, to work on this.
That's amazing. Wow. What a story. I love this for so many reasons. I mean, for one thing, like, I love Japan. It's on my bucket list to go there someday. It's going to happen. But also just, we love collaborative relationships.
Yep.
And that is something that is just really, like, near and dear to my heart, is when, like, people's passions intersect. Just, like, gives me all of the world's warm fuzzies and just makes me so happy. It brings joy to my heart. So that is obviously a great benefit out of something very sad. So then moving on to you actually stepping into this research, I have two kind of related questions. So one is just the background general question of, like, cesium is probably not something that the average person is super familiar with as an element. So can you tell us kind of some background on what is the deal with cesium, like what it is for, what it does regularly, and then obviously you have kind of this radioactive version. And then also just kind of an overview of the general issue that you were hoping to address with your research?
Sure. So I will tell you that before I started working on this, cesium was not something I knew very much about either. It's not an element that people come into contact with in their daily lives, right? So it's cesium is there is naturally occurring cesium, but for the vast majority of cesium on Earth, it's mostly produced in nuclear power plants. It's a byproduct of nuclear power plants. And so it's not something that is commonly occurring. And where we have cesium in the environment, it's usually because something went wrong in terms of a nuclear power plant's waste products, or there was some kind of an accident. So a really good example of where there's a cesium plume in the U.S. is there's one at Savannah River, which there was a lot of nuclear research done there. And then the one at Hanford in Washington State is another big one. So that is where they stored nuclear weapons material, and there were leaks. And so, there's a groundwater plume that's contaminated, not just with cesium, with all sorts of things, but cesium being one of the issues. Sure.
And then can you describe more about the general research problem?
Sure. So the main problem is the deposition of cesium onto the soil, right? So we had these particulates that went up into the atmosphere. Eventually they fell down, and the vast majority of them fell in this smallish area downwind of the power plant. And so when chemicals get deposited or spilled onto the soil, there's two main options for what can happen. So they have a choice. They can either, and I'm anthropomorphizing a little bit, but it's how I like to explain things. So the cesium has a choice, right? It can either hang out with the soil grains, so the solid part of the soil, or it can hang out with the water, right? So everything that's in the soil has this kind of tension, this choice. Where does it want to be? What environment does it prefer? Does it want to be with the solids? Does it want to be with the water? So under normal circumstances, cesium, just due to its atomic properties, it likes to be in water. It really doesn't like to stick to the soil very much under normal circumstances. So most of the research into cesium pollution has focused on groundwater and how to stop cesium from spreading. So when you have a pollutant that likes the water the way cesium does, as the groundwater moves, it carries the pollution with it and it spreads it. And that is a big problem, right? So if the pollution is spreading, then it's contaminating a larger area, and that's something that you want to try and prevent. So in the case of Fukushima, the exact opposite happened. So there's this particular kind of mineral in the soil in that region of Japan called vermiculite. And it's a clay that just happens to really, really like cesium, and cesium really, really likes this clay. So even though cesium doesn't usually like to hang out with the soil solids, when this particular mineral is in the soil, they are best buddies, and they like to be together. So when cesium comes into contact with vermiculite, it binds to the vermiculite really, really tightly, and then you can't get it out. And that is the really big problem. And what makes it even worse is that in this case, we're not just talking about regular cesium, which is already bad. We're talking about radioactive cesium. So when the cesium sticks to the solid grains in the soil near the surface where it was deposited, that is a really big issue, because that cesium is releasing radiation, and any organism, right, people, animals, all sorts of things that come into contact with that soil are exposed to that radiation. So what I'm trying to do is I'm trying to figure out how we can break that bond between the cesium and the vermiculite and get that cesium out of the soil so that we can dispose of it safely.
Hi everyone, I hope you're enjoying the show. Interested in learning more? Dan's article, The Impact of pH and Ion Exchange on Cesium-133 Absorption on Vermiculite, published in the Journal of Environmental Quality, will be freely available for the next 2 weeks. The CSA News article, Farming in Fukushima 1 Decade After Nuclear Disaster, will also be freely available through the end of March. The societies will be publishing related blog posts, which will always be freely available. You can find links to all of these resources in our show notes. If you are a certified crop advisor or certified professional soil scientist, you can take a quiz for continuing education units for this episode, which can be found in our show notes or on certifiedcropadvisor.org. Thanks again also to our sponsors, Meter Group and Gasmet Technologies. Meter specializes in robust soil moisture sensing, innovative weather monitoring, cloud data logging, advanced data visualization software, and more. Their well-published scientific instrumentation is used worldwide in universities, research and testing labs, government agencies, agriculture, and industrial applications. Find world-class webinars about the science behind environmental measurements at metergroup.com/fieldlabearth. For Gasmet Technologies, conduct greenhouse gas flux measurements in the field using the GT5000 Terra. Weighing 20.7 pounds, splash-proof IP54 rated, internal pump and battery, and vibration resistant, the GT5000 Terra is a robust and portable multi-gas analyzer for fieldwork. Visit www.gasmat.com or email sales@gasmat.com for more information. Thank you for being our sponsor. Let's get back to the show. Sure. And you had two kind of paired experiments here that you were doing to work on kind of figuring out the extent of these bonds and, you know, working towards that eventual goal of removing the cesium from the soil. Right. So can you tell me about those?
Sure. So the first step in figuring out a solution to the problem is to really understand what the problem is. And so what we wanted to do was we wanted to get a better idea of what was going on with this relationship between cesium and vermiculite. So there were two basic tests that we wanted to run that would give us some information that would let us better understand what was going on at an atomic level. So the first test that we did is called an X-ray diffraction study. And basically what this is you're shooting X-rays at the vermiculite, and those X-rays bounce off, and the way in which they bounce can tell you something about the structure of the vermiculite. So vermiculite basically is a series of crystalline sheets. So you can think of it like a stack of printer paper, and each one of those sheets of paper is a crystalline sheet of mineral, and they're just kind of stacked on top of each other. And there are spaces in between these sheets which are called the interlayer. So the interlayer is basically the space between the sheets in that stack of paper. Now, the size of that spacing between the sheets changes depending on the environment that the vermiculite is in, how wet it is, what kind of chemicals are around it. But the larger the space between the sheets, the easier it is for chemicals to kind of move in and out of this thing, right? So if you wanted to think of, for example, you have some marbles, and you're trying to get the marbles in and out of this stack of printer paper. Well, if the sheets of printer paper are, 6 inches apart from each other, that marble's going to slide in and out between the sheets really easily. But if the sheets are collapsed, so if I push that stack down and I pack those sheets tightly together, getting marbles in between the sheets is going to be really hard because there's just not enough space. So what we found when we did this XRD study of the vermiculite is we looked at vermiculite that just had water around it, and then we looked at vermiculite that was exposed to cesium. And what we found is that when you add that cesium into the equation, the space between those sheets collapses by 67%. And that spacing in between the sheets is actually smaller than the size of the cesium atom, which means once that cesium gets in, it's not coming out again. So the other test that we did to try and kind of explore this interaction between the cesium and the vermiculite is called an adsorption envelope. So basically what this does is it's a way of looking at how much the cesium and the vermiculite like each other. How strong is that bond, and how hard is it to break? So I've been doing adsorption envelopes since I started my PhD way back in 2008. I've done dozens of these things with different pairings of minerals and ions, and I have never seen anything like what we saw in the bond between cesium and vermiculite. That relationship between those two is so strong that it became almost impossible to split them apart.
Sure. And I know in your worksheet you sent me, you were talking about the way that you do these adsorption envelopes is you just kind of like put in another element that is like fighting to hang out with the vermiculite.
Exactly.
Can you talk about that a little bit more? I thought that was really interesting.
So essentially what you do with an adsorption envelope is you put the element that you're interested in with this mineral, and then you add other competing ions, right? So the cesium has bound to the vermiculite. Now what I'm going to do is I'm going to throw another element into the mix that also wants to bond with the vermiculite and basically see how well cesium does at fighting against it, right? So they're going to compete for who gets to be with the vermiculite. And then what you can do is you can increase the amount of that competing element. So I'm going to start off with a lot of cesium and a little bit of the competitor and see how cesium does. Then I'm going to increase the amount of the competitor a little bit, see how cesium does. Then I'm going to increase it a little more, see how cesium does. And as we increase the amount of the competitor, basically what we're doing is we're making the cesium fight harder and harder to keep that bond. And so what we want to see is we want to see how does the amount of cesium that manages to maintain this bond to the vermiculite change as we increase the amount of that competing ion. So in the case of the experiment that we did with cesium and vermiculite, we used hydrogen. So basically we just kept adding acid, more and more and more acid to the solution so that there were more and more hydrogens fighting against the cesium ions for those limited number of spaces to hang out with the vermiculite. And it was really crazy. So what we found is that at the low concentrations of hydrogen, they were able to knock out a few of the cesium atoms, not very many. And then we reached a point where we kept adding more hydrogen and more hydrogen and more hydrogen, and the amount of cesium that was with the vermiculite just stopped changing. No matter how much hydrogen we threw at it, the amount of cesium stayed the same. So at the farthest end of our experiment, so to speak, we had 5 times as many hydrogen atoms in the system as we had cesium, and the amount of cesium didn't change.
That is wild. And like, I just listening to this description, I'm floored by like, how metal it sounds to be like, we were just like throwing a bunch of acid in there. I just really like that. But like also the fact that you can like tell, to that degree of specificity, like how much was getting knocked off at kind of that atomic level is just astonishing to me. So this research is very interesting and exciting. I will try to contain my excitement. But I did have a kind of a sidebar question here. So obviously the cesium 137, right? That you're talking about here, that is that radioactive material, is like probably not the best to be like hanging out with as a human all the time. So my question is like, how do you go about handling this research with radioactive materials? Like, are you actually working with radioactive materials, or are you just doing this with regular cesium and then are just like, it doesn't, like, the radioactiveness doesn't matter? Like, how does all of that work? And also specifically with like permissions to get access if you are working with the radioactive materials.
All right, so this particular experiment was done with cesium-133, which is the stable isotope of cesium. So it's the non-radioactive one. So for this research, as much as possible, we try and work with the safe one. Or the safer one, I should say, because it's still not, I mean, you know, if you drank it, you would be in trouble, right? But the stable isotope, because it's not radioactive, is much safer to work with. And so when we're trying to do these kind of preliminary studies, we're working with the stable isotope that's not radioactive. Now, I do have Fukushima soil in my lab. So we do experiments with the actual radioactive soil when we have to. And it's a long procedure to actually get the permission to be able to do this. So first I had to get permission from my university, which actually was not as hard as I thought it was going to be. I went into this with this whole big speech planned, and the health and safety guy was like, look, I understand it's important. If we can do it safely, then we'll help you do it. And which was really, really nice. So that was what I thought was going to be the hardest part. Then we had to apply for a permit from the Department of Agriculture to bring foreign soil into the U.S., which also was actually not as difficult as you would think. Then we have to deal with the radioactivity. So radioactivity is governed by the Department of Energy, and I started doing research into what the regulations are in terms of having radioactive material in a university laboratory space. And it turned out that the Department of Energy actually has this limit that as long as you're below that limit, as long as there's less than such and such amount of radiation, you don't need a special permit, you don't need radiation controls. And so basically what that does is it limits the amount of soil that I can have in my lab at any one time. So I can't, in order to stay underneath that limit, I have to basically make sure that I don't have more than about a kilo, so about a little less than 2.5 pounds of soil in the lab at any time. And obviously, as you can imagine, that presents some difficulties because I go through the soil. Once we start doing that research, I'll go through 2 pounds of soil relatively quickly, and then I have to get more from Japan, and then I use that, and then I have to get more, and it's kind of a pain, but this is how we have to do it in order to be able to do it safely.
Wow, that is wild. I'm so impressed by that. And like, so is it so how do you store it then? Is it just like in a lead box, or how does that work?
So with the levels of radioactivity that we have, we don't need any special radiation protection. We have a dosimeter that I keep in the lab, and essentially what that does is it monitors for the ambient radiation level, and as long as that level of radiation stays below a certain point, then we're fine. We don't have to worry about anything. And like I said, the amount of radiation that's coming out of the soil that we're working with is relatively minimal. I actually did this calculation for a grant proposal because I submitted a grant proposal that I wanted to take students to Fukushima. And the grant reviewers were like, "Are you out of your mind? You're going to take students into
Oh,
a
no.
radioactive soil environment. And I was like, okay, hold on. Obviously, I have to put this in context, right? Because people hear the word radiation and they just immediately start freaking out. So the amount of radiation that is coming off of this soil, you would have to have this soil basically in direct contact with you for I think it was something like 100 days in order for it to equal the same amount of radiation that you get during a dental x-ray.
Wow. Okay.
So it's if you're working with it for a few hours a week, it's not a big deal. Okay. It is a big deal for the people who live there, because if you're exposed to it 24 hours a day, 7 days a week, 365 days a year, then it starts to add up, right? Like, you don't want to sit there and get 4 extra dental x-rays a year that you don't need. So, but for our purposes, for the amount of soil that we're working with, it's a relatively low amount of radiation. And when I rewrote the grant proposal, what I said that I hoped would set the reviewers' minds at ease is you actually would get more exposed to more radiation on the transpolar flight from Atlanta to Japan than you would if you were in contact with that soil for the entire 3 weeks that I was proposing for my study. Yeah. So when you fly over the North Pole, or the South Pole for that matter, you get exposed to kind of extra radiation because the barrier that protects us from solar radiation is thinner at the poles than it is in normal parts of the planet. And so, yeah, you actually get more radiation on the airplane flying to Japan and back than you would in 3 weeks of exposure to this soil.
Wow. Okay. Yeah. I'm learning a lot here. I have to admit, I'd probably still be like the lab assistant who's like, I'll just work like on the other side of the lab.
Yeah.
Just can't help certain things. But that is good to know. Glad you guys are keeping safe. So I think we've already touched on results here. So if you don't have anything else to add there, feel free if you do. I do want to ask you about kind of the future research. So obviously you have determined that vermiculite and cesium are best buds for life.
Yeah.
So that obviously leaves the problem of how to get the marbles out of your smashed, lumpy stack of paper. So what is going on there? Like, where are we headed? Are we close? Can you tell me more about where we're going?
So I have been I've been working on a method to try and get the cesium out of the soil for about 3 years now, and it's gone a lot. It's taken a lot more time and effort than I thought it would. I mean, you always go into these kind of things with, well, hey, I'm going to make this plan and I'm going to do this and then I'm going to do that and then this is going to happen and then boom. And that's, you would figure by this point in my career that I wouldn't be so naive anymore. But yeah, research never goes the way you think it is. So you start off with this plan and then there's all these speed bumps that you didn't know were there and that you didn't anticipate that you have to deal with. So I'm 3 years into this thing now and I'm actually getting very close. So we are probably maybe a couple of months from being able to demonstrate proof of concept for this remediation strategy that I've been developing. I'm so excited to actually be able to, publish these results. But so thus far with the method that I've developed, we have been able to get somewhere around 20% of the radiocesium out of the soil, which is a big deal considering that you're not supposed to be able to get it out at all. And so the fact that we've been able to get 20% out is showing that it can be done, which is important. And then once we finish that proof of concept, then the next step is to see, okay, well, we were able to get 20% out. What can we do to increase that number? And the ultimate goal is to be able to get enough radiocesium out of the soil that the soil can be disposed of more easily. So when the Japanese government came in to rehabilitate these areas that were contaminated, basically what they did is they came in with bulldozers and they scraped off the topsoil and they put it in bags and then they just took it away. But the problem is that they don't have anywhere to put it. So they have something on the order of 20 million cubic meters of contaminated soil, which just to put that in context, okay? If we had a football field and we poured soil across that entire football field to a depth of about 3 feet, 1 meter, okay, 3.3 feet, that would be 5,350 cubic meters of soil. So in order to hold the amount of contaminated soil that the Japanese government removed from this area, we would need 3,700 football fields, all filled with soil to a depth of 3 feet to hold it. So, yeah, it's a massive, massive problem. So just to deal with that soil is a huge issue. And the Japanese government has said that they want to build a special facility because wherever you're going to dispose of this stuff, you can't put this stuff in the landfill, right? Like across the street from where people live, that's not going to work. It's radioactive. So you have to build a special facility that can contain the radiation. And they've said, the Japanese government has said that it might take them as long as 30 years to find a place, build the facility, and actually be ready to store this stuff. And that's a long time of this material sitting in some interim facility, not safely disposed of. So what we want to be able to do is get enough of the radioactive material out of the soil so that the soil is less dangerous and can be disposed of in a normal landfill. So in order to do that, based on the regulations that the Japanese Ministry of the Environment has set, we would have to get about 90% of the radioactive cesium out of the soil. And essentially what we then want to do is we want to be able to get that radioactive cesium out and concentrate it down so that instead of having 3,700 football fields of slightly radioactive soil, you're only going to have maybe 100 football fields of super, super radioactive stuff that then would be much easier, right, to construct that facility to hold that amount than it would to hold the whole thing. So, like I said, right now we're just finishing up our proof of concept that this actually works. And then the next step after that is to try and figure out how we get from 20% to 90%. And I have some ideas on how to do that, but I haven't started working on those yet. So I don't know what speed bumps are going to show up and derail me for another 3 years. So my hope is that in another maybe 2 years or so, I'll have enough information to show that this method has the capacity to get the 90% of the radiocesium out, and then I can go to Japan, take it to the Japanese government, and say, look, I've developed this thing. I think it's going to help. Let's try it. And hopefully I can go to Japan on sabbatical, which is my plan, and then I'll have enough time to actually sit down and work with more than 2 pounds of soil at a time, right? And see if I can make this work on a larger scale.
Sure. Wow, what a hopeful outlook. That is really awesome. Congratulations on being so close and overcoming all of the speed bumps. Obviously, it's crucial work that you are doing. Very important. I have like a zillion questions that I want to ask about your research, but We are running a little short on time here, so I will refrain, and maybe we'll just have you on another time, and I can continue to relentlessly pick your brain.
Sure.
Yeah, I would love that. But for today, we're going to finish off with 3 last questions here. First question is, if people want to learn more about any of the things we've talked about today, where can they go to learn more?
Sure. So, as I said at the beginning, this March 11th is the 10th anniversary of the Fukushima disaster. So there's almost certain to be news coverage around that 10th anniversary. And so if people just kind of keep their eyes peeled, I'm sure that they'll find plenty of information in the news media about the disaster and where we are now. If they want to learn more specifically about what's going on in those farming areas that were impacted by the radiocesium, I highly recommend that they check out this nonprofit group that is headed up by one of my Japanese colleagues, Dr. Mizoguchi from the University of Tokyo. It's called Resurrection of Fukushima. And so if you just type Resurrection of Fukushima into Google, that will take you to their website, and you can kind of see some of the work that they're doing. So this nonprofit basically was set up to kind of help fund research into helping these farmers kind of rebuild their lives and recover from the disaster.
Great. Yeah, that makes me really happy that work is being done. So thank you for sharing that. We will include links in our show notes for sure. Second question is, if people then want to take that next step and get involved, how can they do that?
Sure. So they could always donate to Resurrection of Fukushima. So I know that that they're always kind of looking for funding to try and help these farmers more. So and there are other Japanese nonprofits that are also kind of working to deal with the consequences of the disaster. Another thing that I would say would be very helpful is that if you are a soon-to-be college student, or if you have a family member who's going off to college soon, encourage them to study soil. So soil, in my opinion, does not get the respect that it deserves. We need more people in the field studying soil. Soil is the basis of all life on Earth, and I don't think that the vast majority of the population really understands soil to the degree that they should, which is why I teach this stuff, right? Because I'm trying to help remedy that situation. So we need more talented young people who are passionate about the environment to get involved with soil and focus on soil and do research in that area. So I will say, if any of your listeners, if you happen to live in Georgia, come to KSU, come talk to me, come register for my classes, come study soils with me. I teach at Kennesaw State University here in Kennesaw, Georgia. So I'm always happy to have more people signing up for my classes.
Sure. Yeah, it comes up a lot on our show that soil is like really, really important. And the longer I do the show, the more I realize that myself. So thank you for doing the work that you're doing there as well. And then finally, what is one fun fact that listeners would not know about you if all they had was your research?
So I've actually been asked this question before, and my go-to answer for that is that I am a karaoke superstar, and I have the business cards to prove it. And your listeners won't be able to see it, but I'm actually showing you right now.
Oh my gosh, that's amazing.
Maybe I'll send you a picture to include with your article. So a friend made those for me as a gag gift for Christmas one year. And it was not a gag gift to me. I carry those in my wallet.
That's amazing.
So that I can show people I have proof.
So is Dead or Alive your go-to?
That is always the song I sing first at karaoke. It is my go-to song, Wanted Dead or Alive by Bon Jovi.
Okay. For the listeners, that was printed explicitly on the card. That was not just a fantastically lucky guess from me on that. Yeah, I would love a picture we can share with the listeners. That's
Sure.
amazing. I love it. Were you able to do any karaoke in Japan? I hear they've got like a pretty slamming karaoke scene over there.
I have not had a chance to do that yet, but I actually have I'm the program coordinator for a study abroad program at my university to take students to Japan. And unfortunately, we weren't able to go last year, which was supposed to be our first year. And then, COVID happened. And it's looks like we're not going to go this year either, but hopefully next year will be the year that we'll get to go. And I'm hopeful that when I'm there on the study abroad, I'll be able to find some brave students among the people who come, and we'll go find a karaoke bar near our hotel and go do some karaoke.
Oh, that sounds so fun. Well, wow, what a great conversation we've had. Obviously very important work, extremely knowledgeable, and very good at talking down to my level. So that is greatly appreciated. So thank you so much for walking me through all of this today. Thanks for everything you're doing. Best wishes on future research, and maybe we will have you on again to tell us about your future successes. Thanks for being on the show.
Very welcome. It's been my pleasure.
Great. Thank you for listening to Field Lab Earth. You'll find links to today's resources in our show notes or on our website. If you have any questions, comments, or recommendations for show topics, please contact us at podcast@sciencesocieties.org or on Twitter @FieldLabEarth. If you'd like to hear more content like this, please subscribe, and don't forget to rate and review us on Apple Podcasts, Podchaser, Stitcher, or anywhere else you find your podcasts if you like our show. We're also available on Lyceum, the world's first audio learning community, where you can join our discussion group and comment on each episode. This podcast is a joint production of the American Society of Agronomy, Crop Science Society of America, and Soil Science Society of America. Special thanks to Lobo Loco for the use of their song Spook Castle on the intro and outro of our show. Opinions and conclusions expressed by guests are their own and are not considered as those of the American Society of Agronomy, Crop Science Society of America, Soil Science Society of America, its staff, its members, or its advertisers.